Our planet, so much of it covered by water, holds secrets that we are only just beginning to comprehend. We think of rivers as features of the land, carving their way through mountains, meandering across plains, and emptying into the vastness of the sea. But what if I told you that this is only part of the story? What if rivers also exist where we least expect them, flowing silently and unseen in the profound darkness of the ocean deep? It is a concept that seems to defy logic, a paradox of nature. Yet deep beneath the waves, in a world of crushing pressure and eternal night, there are indeed rivers. How is such a thing possible? How can a body of water flow distinct and separate within another much larger body of water? The answer lies in a fundamental principle of physics: density. It is the same principle that allows oil to float on water. It is the same principle that lets a hot air balloon rise into the sky. In the ocean, water is not uniform. Its properties can change dramatically from one place to another, influenced by temperature, and most crucially, by salinity, the amount of dissolved salt it contains. When a body of water is significantly saltier, and therefore denser than surrounding water, it behaves in a remarkable way. It becomes heavier. This dense, heavy water sinks. The water that makes up these undersea rivers is unlike any other on the planet. While typical ocean water has a salinity of about 3.5%, the brine in these deep-sea rivers can be 3 times saltier, 4 times saltier, even 8 times saltier. This extreme salinity gives the water incredible density, making it behave like a different liquid. When a submersible approaches one of these brine pools, its instruments register a sharp, clear boundary. On one side is the cold, standard seawater of the deep ocean. On the other is this bizarre, super salty fluid. The interface is so distinct it can create visible ripples, like the surface of a windy lake. This hypersaline water has other strange properties. While the brine rivers themselves are toxic and inhospitable to most forms of life, their edges, the shorelines, are a different story entirely. Here, at the boundary between the deadly brine and the normal seawater, a remarkable and unique ecosystem thrives. It is a world of extreme specialization, where life has adapted to take advantage of the very chemicals that make the river so deadly. Just as a desert oasis concentrates life around a source of water, the banks of these brine rivers concentrate life around a source of chemical energy. It is a thin, fragile ribbon of life, clinging to the edge of a toxic world. The foundation of this ecosystem is not sunlight, which cannot penetrate to these depths, but chemosynthesis. Vast beds of specialized deep-sea mussels are often found clustered thickly along the brine shorelines. While many of these rivers are found in the profound depths of the open ocean, some remarkable examples can be found much closer to shore, in geological formations known as cenotes. Found primarily in Mexico's Yucatan Peninsula, cenotes are natural pits, sinkholes. One of the most famous and visually stunning is Cenote Angelita. To divers, it offers a surreal and accessible glimpse into the world of underwater rivers. It's a place where you can witness this strange layering of water with your own eyes. As a diver descends into the clear, fresh water of the cenote, something extraordinary happens at a depth of about 30 meters. So, back in 2010, scientists exploring the Black Sea made a discovery that reshaped our whole understanding of the scale of these underwater phenomena. Using robotic submersibles, they mapped out a vast, active channel on the seabed, a colossal underwater river. Not a small trickling seep, this was immense. The channel is up to 1 kilometer wide in places, and its banks rise as high as 35 meters. If it were on land, the flow is staggering, about 22,000 cubic meters per second. That's 350 times the River Thames, a torrent in the deep. The paths taken by these underwater rivers aren't random at all. They're often guided by ghosts of the past, following channels and canyons that were carved millions of years ago, back when sea levels were much lower. During past ice ages, vast amounts of Earth's water were locked up in continental glaciers, which caused global sea levels to drop by more than 100 meters. The river valleys, canyons, deltas were preserved, hidden away in the darkness of the new seabed. These days, when a dense brine river starts flowing across the ocean floor, it naturally finds the path of least resistance. The brine river becomes a successor to the ancient terrestrial river. Despite these incredible discoveries, our exploration of the ocean's hidden rivers has really only just begun. The vast majority of the ocean floor still remains unmapped in high resolution, and we've probably only seen a tiny fraction of the brine flows down there. Charting these features is a monumental task. The main tools for this kind of exploration are autonomous underwater vehicles, AUVs, remotely operated vehicles, ROVs. These robotic explorers are basically our eyes and hands in the deep, able to withstand the immense pressures that would be lethal to humans. AUVs are untethered, pre-programmed submarines on long survey missions. The discovery of rivers flowing in the deep ocean has fundamentally changed how we see our own planet. It's shown us that even in the most seemingly uniform environments, there's this hidden layer of complexity and dynamism that we're only just starting to appreciate. These aren't just geological oddities, they're active, vital components of the Earth system, conduits for energy and chemicals, hubs of unique biodiversity, living archives of our planet's geological past. Their importance goes way beyond their strange, ghostly appearance. They remind us of the profound interconnectedness of our world. They show how processes separated by millions of years can interact to create something new and unexpected.